Okay, so in this video we'll have a couple more sample problems on conservation of mass, but instead focusing on what we can do with that flux term. So that'll be the main focus, the mass flux term. Um, we already had a video here dealing with the unsteady term, and so what I mean by that, this came from a problem that was gone over in a previous video, where we had a system that had gasoline and water, where the water was replacing the gasoline, so the flow was in that direction. And we started here by looking at the full continuity equation. Here's our time rate of change of mass within the control volumes, plus, and then the mass flux term. So the flux is through the control surface. And what we said here was that if, for cases like this where we have an inflow and a single outflow, so a single inflow and a single outflow, where we assume that the velocity is uniform at the inflow and outflow and incompressible fluids, right, so we've made two assumptions. This nicely reduces to not only, well, the change in mass of the control volume with time. That part just is a general statement for what the mass of the control volume is. It's the integral of the density over the control volume. But then we just get that this is just the mass out, the mass flow rate out minus the mass flow rate in, right, at this outflow location and inflow location, right? Well, and then also because it is uniform velocity and compressible, we can just say that this is then not only the mass flow rate, but the mass flow rate is really simply written as density times the volumetric flow rate at each of these two parts. All right, so the mass flow rate of water got moved over here because we put it on the other side of the equation, but the mass flow rate of water is just the density of water times the volumetric flow rate there, and the gas of the water is just the mass flow rate of the gasoline is just the density of the gasoline times its volumetric flow rate. We're going to be a little bit more careful about that and say, what if those assumptions aren't true here? So here's a sample problem I actually just made up. So you're not going to find it in your book, but you'll find something maybe similar. But let's say we have a river, and we want to model, we want to have an analytic relationship for what happens to the flow around bridge, some obstacle in the system. And I have here written, uniformly spaced bridge pillars. So these are, concrete pillars or something that comes to support some bridge. And we want to know what the absolute maximum velocity is in terms of a uniform upstream velocity. So upstream, the velocity is uniform. Probably downstream, it goes back to that uniform flow rate. But at some location here, there's going to be, in localized regions, there's going to be some stronger flow, some higher velocity. So we have a few assumptions here. This is a real river, let's say, but we're going to analyze this by just saying that it's a rectangular shape if we looked at the cross-section of the river, such that the depth of the river is just h, and it's uniform everywhere. And then obviously that this, we're also assuming that this flow profile stays the same as you go down in depth. So in the end, what we're trying to say here is we can do this per unit depth into the page, and it's not going to change anything. Or we can think of this as a 2D river, let's say. So the width of the river is given as L, and it stays the same. That's something else that, in a real system is obviously going to change. But it's also an assumption that the flow is ever uniform anywhere in a real system. But, we can make a pretty good approximation that the river is wide and is just kind of flowing with some uniform velocity. But then these obstacles, modify the flow or interact with the flow quite severely at some locations. It's going to have no flow directly with the obstacle, right? It's going to come to a halt right at that obstacle. And in between the two obstacles, you might expect to see an increase in the flow because the flow has been, the pillars have stopped the flow here, and now the flow has had to squeeze through a smaller area. Well, so that's the conservation of mass principle, is that we can't, if it's an incompressible fluid, you can't have the flow be reduced in a global sense here. If you have this much flow here, it needs to be flowing there. Otherwise, it would need to be compressing or expanding somewhere in between, but this is water we're dealing with and it doesn't expand or compress too easily. So we modeled the profile here through a cosine, where if you look at this, our max, Umax is written here, so this is going to be the maximum velocity achieved for this flow profile, and that's going to come at when cosine becomes -1, right? So cosine goes between 1 and -1, and when cosine is -1, this becomes 1 minus -1, which is 2. So then we have Umax times 2 over 2. This is just Umax. So that's why this is the most. This is the Umax is the maximum velocity in the flow at this location, through our model, and the minimum is going to come when cosine is 1. When cosine is 1, this is just 1 minus 1. That's 0. So that's why we're going from locations of 0 velocity to this Umax velocity. And what we want to know is how much bigger is our max velocity here than it is downstream where we just have constant. Okay. So we start with our continuity equation, and that's going to require drawing the control volume. We've drawn our control volume to be, perpendicular to the flow direction here, so that we get all mass flux entering, where the V dot N essentially becomes, we can pretty just simply replace that with just the velocity. Then we draw our control volume to be right along the shore here so that there's no flow across it in these locations. Okay, so no flow across our control volume there. That makes the second term pretty easy. And then we, again, put it perpendicular to our flow direction here up at the outer edge. And we're not including these pillars in our control volume, right? Although we could, there's nothing going on here, but you might, later on, we might want to know the forces on these pillars, and then that would make it where this choice of the control volume would be smart. Okay, so let's see. This is steady flow, so nothing is changing with time. We took one snapshot in time, and then another snapshot in time. You get no change here. Should also say before we move on. So now there's, I guess this is good. So this part is just 0. Nothing's going to change in time. Right? We're not filling the control volume with more water at one instant time or the other, right? It's just the same, different water particles are flowing through here, but the amount of water inside our control volume remains the same at any time. So we focus our attention on the second term. Well, we have one inflow location and one outflow location. It's this whole entire side and this whole entire side. So we'll label our inflow as 1 and our outflow as 2. So our continuity equation reduces to m dot 1 equals m dot 2. Right, so this is going to be the outflow. The V dot N is going to be positive, and at the inflow, our V dot N is going to be negative. Put 1 on one side, the other on the other side, we get m dot 1 equals m dot 2. So the total mass flux, the total mass flow rates must be equal to each other. Right, but let's be more careful with these mass flow rates. I should say now going forward, here it makes sense to have, at all locations, if we're just going to be limiting ourselves to one, each of the inflow and outflow locations, we can kind of adjust our coordinate systems for the two different places, right? And it's, here we've defined uy to be constant, where y goes this cross stream. Well, if we allow y to also be cross stream here, even though the river has changed and our coordinate system is now looking a little bit different, all we're saying here is that, this was a convenient way to write this, but these y's don't necessarily mean the same coordinate direction for the two different locations. Okay, not a big deal. Just use your common sense on this. All right, so our mass flow rate at 1, we're going to be very careful here. So now we're integrating over the part of the control surface that is just that one location. And it's rho v dot n. Well, v dot n, again, the smart choice of drawing our control surface to be perpendicular to the flow direction allows us to replace this with just the constant u. Let's see, the constant u, big U, right? Incompressible fluid, or at least we can say, definitely we can say that it's incompressible everywhere. So density is constant everywhere. As we'll see in the second example, all we really need to say is that our density is constant along this part of the control surface, right? So anyways, density can be pulled out. Our v dot n now just reduces to big U, and that can be pulled out. And then we're just going to be integrating dA elements, right? Well, this is just going to be the total area. So this just becomes density times the big velocity times the total area, cross-sectional area. Well, that's just the width of the river times the height into the page, which we've just said was just a constant h for our model river here. Okay, so that's a pretty easy one. This is just rho VA, or rho big U times the area, which is L times h, right? That's what you get for the mass flow rate for incompressible and uniform velocity profile. Okay, so the mass flow rate at the second section, though, is going to be a little bit trickier, right? It's still defined in this way, where we're integrating over that, the two segment of our control surface. Well, our density is still constant. It's still incompressible, so we can pull that out. But our v dot n is not just a constant. Well, v dot n is just this u, because everywhere we've drawn our control surface to be perpendicular to the flow. So v dot n just reduces to u, but u is a function of y. So u changes as we integrate along the area, right? So the cross-sectional area we're looking through. Right? So we can plug in u here for v dot n, but we can't pull it out of the integral. Instead, we need to integrate. And our dA elements just become h, constant h, because the velocity, our integrand doesn't change as we change our height down into the page here, or down into the river. But what u does change with is this y, or this cross-stream direction. So our area elements become h times dy. Okay, so now we just have integral of u times h dy. Well, the h can be pulled out. And our y, we're just going to integrate from 0 to L. So from one side of the, one bank to the other, essentially, in y. Plug in what our velocity profile is. It has this cosine. Well, this one part goes to y. The cosine goes to sine, where we have to pull out it's 6 pi over L, but we have to make that inverse for the chain rule to work. So it's L over 6 pi in front. But luckily, sine of, at our two bounds, sine of 0 is just 0, and then sine of 6 pi L over L, so sine of 6 pi itself is also 0. So those cancel. All we're left with is this rho u max h over 2 times this L, right? So our mass flow rate at 1 is rho u LH. Our mass flow rate at 2 is rho u max LH over 2. And setting those equal to each other, right, from our continuity equations, result from our continuity equation, we just get that our maximum velocity at that, the pillar location, the bridge location, becomes 2 times the uniform velocity, right? So as you might, as we expected, and it's a good result here that this is bigger than our uniform velocity, and it being twice as much is just a result of it being a cosine that we use for our model here instead of something more complicated. Note here that the average velocity across all perpendicular to the flow plane, so if you went to any plane that was perpendicular to the flow, that average velocity must remain constant. That's a result of continuity for incompressible flow like this. So the average velocity is just going to be our uniform velocity, right? You took the average velocity across the first segment where it was uniform. Well, that's just going to give you that the average velocity is this big U, and that's going to be our half of our maximum velocity downstream. Okay, so that was the conservation of mass with non-uniform flow profile, but it was an incompressible flow, right, because it was water. So let's do one that has compressible flow where density can change. So our system here is 515. All right, so we got a nice little description that there's a vortex tube shown with hot air entering, and then we have a hot air exit and a cold air exit. And then we have because we just have conservation of mass at our disposal here, we don't have any other fundamental laws to work with at this point. We have to say some other constraints on the system. That we want the mass flow rate of the hot air to equal the mass flow rate of the cold air, and I think I'm going to extend it a little bit more. But here's the, I should show you the diagram that they give, right? So it's basically here. Here's our vortex tube, air entering, hot air exiting, cold air exiting. and that produces a vortex. We'll get to talk about vortices later on in the semester. But just for the conservation of mass on this system, it's nice because we're dealing with air, and therefore we can look at some of the compressible effects. Okay, so our goal here is to obtain exit velocities that are equal, right? So the exit velocities are equal in the hot and cold exits, with also equal mass flow rates. Okay, so that's really all it's saying is let's say that the mass flow rates are equal and that the velocities are equal. We can, though, change, what can we change? Well, I mean, if this was true for an incompressible flow, if they had to have equal mass flow rates and equal velocities, and then the density couldn't change, right? So our mass flow rate is rho VA. Incompressible means rho can't change. We're saying V can't change, and we want the total mass flow rate to change to remain the same. Therefore, the areas had to be the exact same, right? So if rho VA was had to be held fixed, let me just say. So for incompressible, we have this. This is incompressible here. So if this can't change, these two are equal. So that would be a constant in our system, let's say, and we want this to be equal. Better to say, how about this? We want m dot to be equal. We want rho to be equal. And we want V to be equal at the two places, then A had to be equal as well. All right, well, that's not going to be true because our density can change in this case. And, we just saw that perhaps velocity can be non-uniform as well, too, right? So there's some options, there's some different ways to get where m dot is equal, but other things are not true. But for this system, our velocity is going to be the same, but density can now change. So our areas don't necessarily need to be equal for these two constraints to hold true. Our constraints are that with equal exit velocities and equal mass flow rate. Determine what the exit areas need to be. Now I'm also going to add on that if we also say that the inflow velocity must equal the outflow velocities, right? So if the velocities are everywhere the same, velocity here is the same as here and here, what is the cross-sectional area of the inflow part compared to the cold part, right? So this is the exit areas, hot over cold. This is going to be the inflow area to the cold area. Okay, so our conservation of mass, we should start with the full continuity equation here, but we're just going to jump to the part. This is steady, so that unsteady term drops to 0, right? There's any snapshot in time is going to look the exact same. So that part goes away, and then we're just left with, that, oh, sorry, so this actually isn't even the continuity equation yet. We're just saying that, that's right, that's why I wanted to add D in here, because we actually don't even need to use continuity in this case. All we're using here is a definition of mass flow rate. So all this says is that we want equal mass flow rates, hot and cold. So mass flow rate hot equals mass flow rate cold. Therefore, we're assuming uniform velocity profile. And the other assumption here, density can sure change, but it's not going to change at the segments across each segment. So we do have assumptions in here that we have uniform velocity and constant density. And this is across outflow regions or areas. Right, so any of the particular areas of interest, this is true. All right, so even though we have a compressible fluid, and even within the system density can change, what we're saying here is that across the outflow of the hot, density is constant. Across the outflow for the cold part, density is constant. But if we compare here to here, density is definitely changing. Make sense? Okay. We also then impose that the velocities are equal, so VH equals VC. Then we just have, we already have the form of the solution here, that the area for hot over the area for cold, that's what was being asked in the problem statement, is just going to be the density of cold over density of hot. Well, here we're assuming ideal gas for the air involved, or for the gases involved. So therefore, then we're just replacing densities with pressure over RT. The R's are going to cancel on the top and the bottom. So we're just going to have pressure cold over pressure hot times temperature hot over temperature cold. Just plug those in from the problem statement, and we get that the area for the hot must be a little bit smaller than the area for the cold for these constraints to hold true. Okay, I wanted to extend this to include some use of the continuity equation. I thought that it was a bad practice here to start to apply conservation of mass without actually applying it. But you can see we weren't applying conservation of mass here. We were just saying there's a constraint on the system that we want the mass flow rates to be the same. That's just given as a statement, a constraint given for the system. We now need to use conservation of mass, our continuity equation, to actually do part B, which is to say we now want the same velocity in the inflow and the two exit regions. So same velocity at all inflow and outflow regions. Same assumptions are going to hold true here, where we're going to assume uniform velocity and constant density across the outflow. And now I'm going to add also inflow and inflow area. So if you go across any area of interest, across any inflow or outflow area, right, velocities are going to be the same, or assumed to be the same, and density is going to be the same. So here to here, density is the same between these 2 points. Between here and here, the density is the same. Between here and down here, density is the same for those. But if we went from here to over here, density is not the same. And if we went from here down to here, density is not the same. Okay. So our control volume is just going to be all the air in the vortex tube system. It's steady flow, uniform velocity and constant density across inflow and exit regions. That was what I said up above. Steady makes this unsteady term drop out to 0. We just have that the mass fluxes through all of our inflow and outflow regions must sum up to 0. Let's put the inflow on one side of the equation and equal that to the two outflow regions. So m dot in must equal m dot hot plus m dot cold. With those assumptions of constant velocity and constant density across the inflow-outflow regions, we allows us to write all the m dots in terms of rho VA. So rho VA for the inflow equals rho VA for the hot exit plus rho VA for the cold section. Now our constraint that the problem statement asks for, so the design requirement is that the velocities must be equal. That cancels all the velocities. These are all equal now. Right? It's a bit, I'm not sure the application of this, but I just wanted to do something extra to the system to use conservation of mass. All right, so now we have, and then we're going to divide through by the cold area, because this was the answer to our first problem. And now this is going to be the unknown here, right? So we've already, in part A, we solved for this, and now we want to know what this ratio is. So we divide through by the cold area and apply ideal gas to the three densities. All of the terms are going to have an R on the bottom, a gas constant on the bottom. And then we have pressure in, pressure hot, temperature cold, pressure hot, temperature hot, pressure cold, temperature cold. We have all those. Those are all given in the problem statement, and we've determined this to be 0.943 from part A. Solve for the one unknown, right? That's just by plugging everything in, and we get that the cross-sectional area, that the inflow cross-sectional area must be 1.2 times the cold area. So this must be 20% bigger than the cold area, and then it must be even a little bit bigger than the hot area, because the hot area must be a little bit smaller than the cold area. Okay, so in this video we've seen how that flux term, mass flux term, can be used, or can get a little bit more complicated than just rho VA, or for a whole system, even though we're just dealing with one fluid here, the density can change from location to location, but we do need to make the assumption that it's constant across each inflow and outflow region.